what I need to do here is take in a target sum as an argument, as well as an array of numbers. My function needs to return a Boolean, so true or false, indicating whether or not it is possible to generate the target sum using some numbers from the array. Now, along with that, we have some constraints here. We can totally use an element of the array as many times as we want, and we can also assume that all input numbers, so the target sum as well as the numbers of the array, are non-negative. So let's try to understand what this question is asking. Let's say I gave you this example case. So it looks like our target sum is 7, and the array of numbers is 5, 3, 4, and 7. Here, the response should be true because it is possible to generate 7 by adding some amount of numbers from the array. One way you can generate 7 is by just doing 3 plus 4. Another way would actually be to just take the lone 7, because 7 is actually a member of the array. So it's definitely possible to generate 7 using some amount of numbers from the array, so that's why we return true. Let's say I gave you another example. Let's say I gave you a target sum of 7 again, but I gave you a different array of just 2 and 4. This is actually going to return false because there is no possible way that combinations of 2 and 4 can actually sum to 7. Cool. So that's really what the question is asking. Now let's try to think about how we can frame this problem recursively, right? Hopefully you've already gathered in your mind. If we have a smaller amount of target sum, then that'll tend to be a smaller or easier problem than a larger number for target sum. All right, so let's start to think about the recursive structure for the first example. We know in the long run, we should be able to derive the answer true from this drawing that we make. So like we always say, we should encode the arguments to our function into the nodes of our drawing. That being said, since in the problem they told us that we can reuse an element of the numbers array as many times as we need, I'm just going to omit that from the node drawing because basically every node or every function call is going to receive the same array. So I'll just list the target sum in every node. So I start with 7, and I have to think about how I can transition to other nodes, right? How can I shrink the size of this problem? Well, I know that I only have 4 options I can take, right? I have an option for every element of the array. So basically, if I'm at this 7 node top level, I can branch to some children. And sort of the rule for my transition is you can either take a 5, take a 3, take a 4, or take a 7. And if I actually take those elements as a choice, they are going to decrease my current target sum. In other words, 7 minus 5 is 2. 7 minus 3 is 4. 7 minus 4 is 3. And of course, 7 minus 7 is 0. So notice we have a very particular rule from traveling from a parent node to some child. I can just carry over this pattern. However, we have to watch out, right? So let's say I try to flesh out this node where my target sum is 2. If I look at the options I have, right, I still have the options of 5, 3, 4, and 7. However, none of them are really compatible with this target sum of 2. Right, what I don't want to do is take any of these choices because that would kind of give me a negative target sum. So I can't really flesh out this node 2 anymore. That is, there are no valid options for this node. However, some of these other nodes, like this 4, do have valid options. So what I can do is take a 3 or take a 4, and of course I get a 1 and 0 respectively. And I'll also do this for the 3 over here, right? For this 3 node, I can only take a minus 3 as a choice. Cool. If I look at all of the nodes that I have now at like the leaf level, it looks like they all sort of bottom out at a base case. That is, there is no further choices we can take. And I also notice that some of my nodes have a 0 in them. If I look at the nodes that have a 0 in them, they actually are a really nice base case because I basically have found that I can generate the original target sum, right? A way you can kind of understand the base case when the target sum is 0 is you can always generate a sum of 0 by taking no elements from the array. Right, so these 0 nodes are trivially solved, and to me, they should return a true backup to their parent, right? And sort of on the flip side, for all of my nodes that are not 0, and they also can't break down into any further nodes, those return false, right? Because I kind of have a leftover, and I know there are no possible options I can take to reduce that further. So all of these other nodes should return false to their parent. And remember what this question is asking, right? It's really asking, hey, is it possible at all to generate the original target sum? And so the logic is when these values, these Boolean values return to their parent, the parent should just check if at least one of them is true. And if at least one of them is true, then that parent should also return true. And if I look at this 4 node, I have a true above it, and that sort of answers the question, hey, can I generate a sum of 4 using elements of the array? And you totally can, because if you look at the elements of the array, there is exactly 1 4. So I could just take that into my sum. So I'll be sure to bubble up, all these Boolean values to their parent. And again, the parent will just make sure that at least one of the values it gets back is true. And so if at least one of them is true, then the parent itself will also return true. So very reminiscent of some like Fibonacci bubbling up pattern as well as our grid traveler, except now we're kind of adapting this for some Boolean data, but it's really the same structural understanding I have. Cool. So that was an example where we said true right there is a way to generate the sum. But let's look at another example, right? How do we know the flip side? So if we have this example, right, 7 and an array of 2, 4, in the long run, that's going to return false, right? There's no possible way you can generate that target sum of 7. And so the tree for this example would look like this. So this is the full tree. Notice that all of the leaves get as low as 1, but they can't be broken down any further. Like we just said in our last sketch, all of these 1s, since they can't be broken down any further, and they haven't reached a 0, they're going to return a false up to the parent. And I know that if I bubble up all of these false values, of course the top level call will also return false. Right. So it looks like a key insight we have for this problem is if we find at least, one base case that returns true, I know that I can sort of stop early and just return true all the way up to my parent. Because they're not really asking like how many ways can you generate the target sum. They're just asking, hey, yes or no, can you generate the target sum at all? So that's going to be a really nice way to implement this code. I think we're ready to jump right into the code. So let's do it. Okay, so let's go ahead and implement this CANSUM function. So since we're going to solve it recursively, I think a good starting place as always is to maybe handle some of the base cases. So when we drew out the tree, I noticed that one of our base cases was when the target sum reaches the value 0. Right? If our target sum is 0, then we have basically trivially solved the problem because you can definitely always generate the target sum of 0 by taking no numbers from the array, right? So I'm going to return true if ever I reach a 0. Then apart from that, I think let's go ahead and work on the recursive scenario. So I know that I need to establish some logic where I make a recursive call or a branch for every element of the numbers array. So what I'll do is I'll iterate through that array of numbers. So I'll use some for let of syntax. So I'll say let num of the numbers array. So if you're unfamiliar with the syntax, all it does is iterate through every element of the array. So for example, let's say I just called the first example for CANSUM of 7 and an array of 2, 3. If I just console.log the num, then I'm just going to see the elements printed out of 2, 3, right? So I'll give this a quick spot check. Nice, so just iterating through every number of the array, no tricks here. But now that I have that number, I need the branching logic. So remember the logic we used for transitioning from one node of the tree to the next? What we did was subtract our current choice of number from the target sum. And that basically gave us the new target sum. So I'm going to express that in maybe some variable. So I'll say, all right, I'm going to generate the remainder by calculating the difference between the target sum and the number, right? So I'm just subtracting the number from my target sum. That gives me my new remainder, which becomes a target sum, right? So at this point, I think I need to call recursively on CANSUM, but I'll pass in this remaining quantity. It does need a second argument still. I'm still going to pass in the same exact numbers array. So I'll still pass in numbers unchanged. I think that the fact that we pass in the same exact numbers array is pretty consistent with the way they stated the problem because we can totally reuse the numbers of the array as many times as we like. Cool. So now that I'm using our function again, I'm making the recursive call, I want to think about what this call will return. I know at any point in time, my CANSUM function is going to return Boolean. And what's great about Boolean data is there's only two possibilities, right? It's either true or false. So I think based on what we said about the tree was, if this call, if that returns true, then I can just ultimately respond with a true right now. So I'll write it like this. So this is saying, all right, if we figure out that it is possible to generate the remainder using numbers of the array, then I can return true for this larger problem of target sum. Right? So if I find at least one way that works out, then I'm going to do an early return true. And the really important pattern here is we don't want to write the else and then return false. Instead, we'll want to return false after the for loop. And so here's the reason why we want to return false after the for loop. I only know that after I attempted, all possibilities and I found that none of them worked out, can I actually say that it is impossible to generate the target sum, right? So I need to make sure that this for loop tries all possibilities of number before I can say false, the target sum cannot be generated. That being said, there's one thing we should add to our code. So if you look at line 6, right, I'm subtracting our choice of num from the target sum. And that means that sometimes the remainder might become negative. So remember in our tree structure, we made sure to sort of return a false whenever we had some node that didn't do any branching. To kind of account for that, I can kind of bake that into another base case. But this time, make sure it doesn't return true. So I'll say, if my target sum is negative, so if it's less than 0, then you've gone too far and you can just return false. Here it's safe to just automatically return false if your target sum hits something less than 0 because you've gone too far and there's really nothing else you can add from the numbers array to ever fix that negative target sum. Remember, they told us in the problem that your numbers are always going to be provided as positive numbers or just 0, right? So let's go ahead and give this a go. So I'll try all of these examples and we'll see what we get. So I expect a true, true, false, true, false. Cool, so it looks like a few of them are working, right? It looks like the first 4 are working totally fine. But it looks like on that last example, my program's still running. And if you notice, I chose a pretty large value for m. So kind of like we expect, this solution has correctness, but it possibly lacks some efficiency. It looks like it just finished. That definitely took way too long. And so this is a very interesting example of a slow input to CANSUM because for one, the length of the array is pretty short. I only gave 2 elements here, but it seems like this number as a target sum really affected the runtime. So here's what we'll do. Let's head back to the drawing board and talk about the complexity of this baseline solution. All right, so we implemented the brute force for our CANSUM, but obviously now we want to make it a little faster. But before we kind of just jump into memoizing the solution, let's at least describe the complexity of our current brute force. So let's try to visualize this example. So I have a target sum of 8, and my choices for my numbers are 2, 3, and 5. In the long run, this should return true. The visual for the full tree would look something like this. Notice that it's a fairly large tree for some relatively small inputs, right? I only have a target sum of 8 and only 3 choices. So let's try to describe the complexity of this. I'll sort of generalize the shape of it, get rid of those numbers. So this is the overall shape of the tree. And I know I want to describe my complexity in terms of the input to my function. This function has 2 inputs though, right? I'll say that m is the size of the target sum, and n is the length of the array I'm given. I know that both of these arguments definitely have an effect on the dimensions of this tree. So like we did in all of our other examples, I'll start by maybe analyzing the height of this tree. That is, what would be the maximal distance from the top level call to a base case? Or in the structure of the tree, what is the maximal distance from the root of the tree to the farthest leaf? So if you sort of imagine that we have m as the root of the tree, imagine that along the left-hand path, we just did a -1 all the way down, right? So we kept taking a -1, right? In the worst case, maybe there's a -1 present in our numbers array. In the worst case, the distance from the root to a base case would be exactly m, because you have to subtract 1 m times, right? So I can basically say that the height of this tree is m. And kind of like we said in our other problems, that means that the number of levels is m, right? So now that I've identified the height of this tree, the move is now to identify the branching factor. That is, how does the number of nodes change from one level to the next? Remember that initially we described this particular tree example as having a numbers array length of 3. And you'll notice that the maximal branching factor is exactly 3, or in general, n, right? Because n is the length of the array. So for example, if I had 3 numbers in the array, then a node would have at most 3 children, right? Because you have 3 options to take. We've seen this pattern before. I have m levels, and from one level to the next, I would multiply the number of nodes by n, right? This is the same thing as saying, hey, we take n and multiply it by itself m times. And this would definitely give us an exponential complexity, right? In particular, n to the m time complexity. And like we always say, another great thing about this type of diagram is we can also derive the space complexity, right? So what would be the space used by the call stack it would really just be the height of the tree, which we already described as m. So overall, our brute force is looking at an n to the m time complexity and m space complexity. So now that we actually have, those concrete numbers for our complexity, let's go ahead and focus on how we can truly improve this. So here's again the drawing for this particular example. It's a fairly large one, and typically, when you're trying to notice where there is room to be optimized, you might have to give yourself a sufficiently large example to see these scenarios. So in this example, I do have overlapping subproblems, and in the context of my tree, that means I have duplicate subtrees. So I can look at possibly this subtree rooted at 3. Notice that the root of that subtree is trying to answer the question, hey, can I generate a target sum of 3 using the array? And of course, once you find that answer is never going to change for your target sum of 3, right? So I know that all 3 of these subtrees are trying to ask the same problem. And so what I'll do is I'll just cache those results in my memo object like we always do. So let's go ahead and work on that. All right, welcome back to my code editor, and same stuff, different day. Let's go ahead and memoize this CanSum function, right? Once we've established the brute force through the recursion, then memoization is pretty formulaic, right? All right, so we'll start by just baking in our memo object like we usually do. So if someone calls our function without a third argument, that is like a top level call, we'll be sure to give them a new object. And before I forget, be sure to pass down this memo object. So I'm going to make sure that every top level call in its recursive tree shares the same memo object. But now I need to figure out what should I use to key into the memo object. So here I have 2 arguments of my original function, right? I have target sum and then numbers. What I want to do is try to notice which of these arguments is actually going to directly impact the return value. So I know that through the recursive calls, like this call over here, the numbers argument doesn't change. And so if it doesn't change, then right now it doesn't really affect the return value. So I'd be okay to just use the target sum as the key into this memo. So I'll go ahead and do that. So I'll check if my target sum is in the memo. Then I've seen that subproblem before, so I can just return the stored value. Cool. And now I have my memo fetching logic. But now I need to actually store things in the memo. And the trick is, what I want to do is look at all of the return values that were not base cases, and I need to now store them in my memo. So I have 2 return values here, right? These 2 lines 10 and 14. And so I need to store data into the memo for both of those lines. It's as simple as quite literally going into your memo, using your key, so target sum, and then assigning the value you just returned. So I'll just write it like this. And this is going to be sort of a hard and fast rule you can always use for memoizing a brute force recursive function, right? So I'm just going to take exactly the lines or the expressions that I returned in the recursive scenarios and now just store them in the memo. Cool. So let's go ahead and give this a shot. This code is looking pretty good. And remember before, this last call with an input of target sum 300 took noticeably long. But I think now when I give this a shot, right, it finishes really quick. So this is going to be a nice optimized solution for CanSum. Really, most of the work of this problem was done in the brute force, and then afterwards, it's really just a minor adjustment to make it efficient. So to wrap up this problem, let's go ahead back to the drawing board and talk about the improved complexity. So we definitely memoized the heck out of that code, but let's recap by just understanding what the new complexity is. So again, we're saying that m is the target sum and n is the length of the array. Initially, we said that our brute force solution had an n to the m time complexity, which is exponential. And actually, once we memoized it, we really cut down on that complexity. We brought it down to an m times n time complexity. And so here we say that the memoized complexity is now m times n because of the memo object, right? We know that the value of the nodes in the tree are just going to be values up to m, right? There are m different possible values that we can have in a node. However, now since we are able to cache values or cache results inside of the memo object, I'm never going to have to re-explore a subtree for m. That being said, I still have to branch n times for each of those nodes, right? So overall, I have m times n nodes. So hopefully that CanSum problem made some sense, because what we want to do now is actually carry over a lot of that knowledge to solve this new HowSum problem. So this problem is very similar. It still asks us to take in some target sum and an array of numbers. But this time around, what we want to do is return an array containing a combination that adds up to exactly the target sum. And if there's not any combination that actually leads to the target sum, then I should just return null. Along with that, if there are many possible combinations that can reach the target sum, then I can return any of those. So you're probably already recognizing that this how sum problem is very similar in logical structure to the can sum problem, right? Instead of returning a Boolean, instead now I want to return exactly the combination of elements of the numbers array that leads to my target sum. So it's a little more involved. That being said, let's take a look at some examples to make sure we're on the same page. So let's say someone asks us to calculate how sum and our target was 7, and our array of numbers are 5, 3, 4, and 7. So there are actually a few different combinations that can give you your target sum of 7. One way would be to take 3 plus 4. So that's one possible answer. Another possible answer would just be returning an array of 7. So no matter which combination array you return, it'll be considered correct in either scenario. Let's say I gave you another example where your target sum was 8 and your choice of numbers were 2, 3, and 5. One possible solution for a combination is 2 plus 2 plus 2 plus 2, right? So I return that in an array. Another combination would be just 3 plus 5. Notice that no matter what, we're always looking to get back an array if it is possible that our target sum can be generated. But let's look at the flip side. Let's say that we were given this input. So I have a target sum of 7 and my array of numbers is just 2 and 4. The first thing we notice is it is not possible to actually generate the target sum of 7. Like they said in the problem, in this scenario, what you want to do is return null to sort of symbolize that, hey, it's not possible to generate any combination that leads to the target sum. All right, I think it's important that we think about one more scenario. So let's say that I was given a target sum of 0 and we were given really any array of numbers. In this case, I just gave us 1, 2, and 3. We already know that in our previous problem where we had to return a Boolean result, we used the target sum of 0 as a base case. And so what I want to think about now is how is the target sum of 0 just trivially solved? Well, if I want to know the combination that sums to 0, then that's really just the empty combination, right? So I think the logical result here is to return an empty array when your target sum is 0. Remember that an array represents a combination, and if I have an empty array, that means I take no elements into my combination, right? If I summed up all of the elements in that empty array, it would indeed have a sum of 0. So that's going to be a really important facet that we need to encode into our logical tree that we draw out next, as well as our code, right? So let's take a look at how we can structure the tree and try to take a step toward really understanding how we can implement it in some code. So let's say we're stepping through this particular example of target sum of 7, as well as an array of 5, 3, 4, and 7. So the full tree, in really the same tree that we drew last time, would look something like this. From the get-go, I see that I have some scenarios or some nodes where I reach 0, which means that it's definitely possible to generate the target sum. That being said, how can I get back a valid result, right? So I need to return an array. So we sort of reframe this problem in that, all right, all of these base cases that have a target sum of 0, they are trivially solved because their combination would just be the empty array, right? So for now, I'll just kind of trace through how one of these base cases would return. So I know that this particular 0 is going to return an empty array. And like we always say, when it returns, it's really returning that information to its parent, right? So this array sort of bubbles up to its parent. And now what I want to do is actually manipulate this return value. I want to add something to it. So I want to really put the number that brought me to that 0 in the first place. And that would really be the choice of 4. So notice along the edge, I have them labeled with a -4, meaning that, hey, I took a choice of 4. And I want to actually add that choice into the current array. So I'll just really push it into the array. Of course, I actually don't need the negative sign. That was just for the sake of understanding, the math here. But now that my call to how sum of 4 is returning an array of 4, that array bubbles up to its parent. And of course, now I need to push that edge that I took, which would be that 3. So now that 3 gets pushed to the array as well. And if I look at what I'm seeing right now, it looks like above the 7, we have an array of 4, 3, which makes sense because you can totally generate a target sum of 7 by doing 4 plus 3. Awesome. So 4, 3 would be a valid answer in this particular problem. But like they said, you could return really any valid combination if one exists. So let's say we chase through this far right base case. We know that this 0 is going to return an empty array. That empty array will be returned to the parent. But we also have to add the value according to the edge, right? So I would put a 7 in this array. And that makes sense because I could generate the target sum of 7 by just summing up a lone 7. So that's still good to go. So I'm feeling pretty good about how we can return a valid combination if one exists, but let's say there are some options that we take that don't work out. So for example, let's say we explored this node first, right? This was the first base case we hit, and logically in the space of our code, it really would be, right? So I know that this node can't really branch out any further, so it's sort of a dead end. This is a node that should return null, meaning that, hey, there is no way I can generate a target sum of 2 using elements in the array. Right? If you look at the elements of the array, they're all too big, right? So I know that this base case is going to return null. But along with that, if you look at the next base case we would hit, it would be this one, which also returns null. And if you look at the next base case to the right, that's actually an affirmative one that should return an empty array. So let's kind of reason out how these return values should be considered at their parents. So I know that both of these values to the left of the node 4 would return, right? So it kind of bubbles up a little bit. But for the array on the right-hand side, I would also have to push the edge that I took, which was a 4 in this scenario. So now I'm sort of comparing, the null in this 4, or really I'm comparing all of the branches that I take from a node. And if at least one of the branches gives me back an array, then I know that it's possible, right? So basically in this scenario, the array of 4 actually wins out over the null, right? I know it's possible to generate a 4. And I'll just continue this process, right? Now I can return these 2 values to its parent. So let's say I'm considering them at 7. In the same way, I would have to add the edge I took, which would be a 3 on this array. And then from there, I know the array would always override the null, right? So I can just ultimately return this 4, 3. And a really nice pattern in this code is as soon as we find a winning path through the tree, or that is we find a combination that creates the target sum, we can actually return early because we don't need to really travel through the rest of this tree. We don't need to explore any other options because they're happy with at least one combination, right? Awesome. So again, to recap, the punchline is for this tree, I have the information for a combination encoded as a path through edges of this tree, right? So if I look at this path I have highlighted in yellow, I see that I took a 3 followed by a 4, and that eventually led to a 0. So I know that one valid combination would be 4, 3. All right, at this point, I'm feeling pretty good. Let's go ahead and work on the code for this now. All right, here we are back in my code editor, and let's work on solving the howSum implementation. So the code's going to be pretty similar to the CANSUM problem. That's really the whole point. We're just kind of going to finesse the return data over here. So I'm going to have a very similar base case. Like we said in the tree diagram, whenever we have a target sum that's 0, we have trivially solved the problem because I could just return an empty array. In a similar way, what we can do is also have a separate base case. If our target sum ever reaches a negative quantity, then I'll just return null. And that's because it's never possible to generate a negative target sum, right? Remember, in this problem, the array of numbers is only going to be positive ones. Cool. And we ended up writing very similar base cases for our last problem, except now instead of returning true, we return an empty array. And instead of returning false, we return null. Nice. So let's go ahead and get the branching logic, right? How do I want to make my recursive calls? Well, I'm going to need to make a recursive call for every element of the numbers array. So I'll say let num of numbers. So I'm just iterating through every number of this array. And I'll go ahead and do the same logic as last time. So I'll subtract the number from my target sum. That'll give me my remainder, right? So remainder equals target sum minus my number. Cool. So this remainder is now what I want to find the combination for, right? So here I would make my recursive call. So howSum, pass in the remainder, and the second argument will stay exactly the same. I'm going to pass along the same exact numbers array. I don't need to remove anything from the numbers array because they tell us in the problem that we can reuse the elements however we see fit, right? Cool. So now I need to really think about what type howSum returns. So this problem is interesting because we basically have 2 different types, right? We could get back an array of some elements if it is possible to generate the remainder. Or we can get back null when it's not possible to generate the remainder. I think no matter what I get back, I'm just going to save it into a variable. So I'll say const, so this is the result for the remainder. I'll call it remainder result. Cool. So I know that in the context of like how I thought about this logic in terms of the tree, I wanted to basically do an early return if I found a valid combination. And so I'll go ahead and check, if the remainder result is not null. So the implication, if I enter this if statement, that means that it is possible to generate the remainder. And so what I can do is just return early, and I can return basically almost the same remainder result, so the same array. However, I need to make sure I include the element that I took. Recall from the diagram, whenever we had a recursive call that returned an array, the parent had to also add the number that it took to transition to that recursive call in the first place, right? So in the context of the tree, I had to put the labels of the edges into the array. Here, that means I have to put the num into this array. So some syntax I can use for that is to use some spread operator. So I can copy all the elements of the remainder result into this new array, but I'll also add on the number I just took, right? So all I'm doing in this return line is I'm returning basically the same array that I get back from my recursive call with the number added to the end of it. Let's say you're unfamiliar with this syntax. I can preview it really quick. It's pretty neat. Let's hop into the Node REPL. So let's say I had some array. Let's say it was this array of just A, B, C, sort of an isolated example. You can use the spread operator, which is the 3 dots here, to like unpack an array. And you can sort of say like new array equals bracket. So this gives me a new literal array. And I can spread out the elements of the old R, right? So if I do that, the new array just has all of those same elements if I capitalize that properly. Cool. And we can extend that syntax, right? So I still have that array of ABC. Let's say I had another variable, we'll call it other array. What I can do is create a new literal array, copy all the elements from R using the spread operator, and then I can comma separate any additional things I want to add while I'm here. So let's say I added a Z. So if I look at my other array now, it contains A, B, C, and also this new element Z. So it's all I'm doing on this line, right? I'm returning the same combination that my recursive call gives back with the number that I took added to the end of it. Cool. So what's really nice about this code is it's very reminiscent to our previous code because we have an early return. So if I find at least one way to generate the target sum, I can just go ahead and return that first way that I found, right? They say we can return any valid combination here. But let's say this for loop finished and we never found a valid way to generate the target sum. Then after the for loop, you can just return null because it's not possible to generate the target sum apparently. Cool. So this code is looking pretty good. I think let's give it a shot. Goes without saying, sometimes the remainder, right, will become negative, but we already handled that with this nice base case, right? So let's test this code. So I already have some example outputs over here. So it looks like our first few examples are working. Obviously our last one seems to take quite a long time. So I'll just kill this program early. But before we talk about how to optimize for this larger example over here, if you look at these other examples, what I can see is this array of 3, 2, 2 does add to 7, so that's looking good. This array of 4, 3 also adds to 7, so that's good. We already saw that this example of 7 and 2, 4. That should return null because it's not possible to generate that sum. And it looks like the array for the 8 example is also good to go. So notice here, there are also some other arrays that we could have returned and it would still be considered valid output. The exact combinations that we get back are really just dictated by the order that we happen to iterate in the array. So for example, let's say I switch things around here, like I did 3, 5, 2. It's really the same array, just in a different order. We'll probably get a different answer for that particular one, right? So I'll run this now. Notice I get 2, 3, 3. But in either case, that still sums to 8, so we're totally good to go. Awesome. Let me bring this back to the original code. And yeah, it seems that now the limiting factor seems to be the speed of our solution, right? We've been here before. And so let's go ahead and talk about the complexity of it. So we know that the time complexity for this is almost identical to what we did in the CANSUM problem, which is conveniently over here. But let's sort of refresh. By now you recognize that, all right, the time complexity should be described in terms of like the recursive tree. So let's lay down a little foundation. And we already know that M, we're going to call the target sum. And let's also say that N is the numbers dot length. Cool. And so if I think about the number of recursive calls that I'm going to make, it's really the same as last time, right? So I'm going to say that, hey, the time of this function seems to be O. And I have an exponential. The base of the exponent is the branching factor, which is the length of the array. And then the depth of the tree would be the exponent, which is just M, right? So this was the same time complexity as last time for our brute force, right? It's M to the M power. However, it looks like we have some additional time that we consume in this function really coming from this expression, right? So if I look at line 9 in particular, this line creates a copy of an array. So that will actually take sort of a linear number of steps to copy over every element of an array, right? So I will have to consider the cost of this operation. It's sort of under the hood, like iterates through the remainder result. And I know that the maximal length of